In topic 8, we have introduced the use of integer variables to determine if a process unit or process option is selected or not. We then develop mathematical formulations for optimization of process synthesis problems to determine the best flowsheet structure. Then we define the optimization problems for process synthesis problems as mixed integer programming optimization problems, including mixed integer linear programming and mixed integer nonlinear programming problems. In the mixed integer linear programming, the object function is linear, constraints are linear, some variables are continuous variables, some variables are integer variables. In the mixed integer nonlinear programming, the object function and or at least one of the constraints is nonlinear. Some variables are continuous, some variables are integer variables. If all variables are integer in the mixed integer linear programming, it is called integer programming. In this topic, we will introduce optimization methods that can be used to solve these integer programming and mixed integer programming optimization problems. We first talk about the branch and bound method. Then we will introduce two different branching strategies. They are depth first strategy and breadth first strategy. And then we will discuss how to use the branch and bound method to solve mixed integer linear programming problems and also mixed integer nonlinear programming problems. We will also introduce other optimization methods that can be used to solve mixed integer nonlinear programming optimization problems. As we have defined mixed integer linear programming, mixed integer nonlinear programming, and integer programming problems, we first focus on integer programming and mixed integer linear programming problems. This is because in these problems, the objective function and constraints are linear. How can we solve integer programming and mixed integer linear programming problems? Can we use the Lagrange multiplier method? We cannot, right? This is because in these problems, we have integer variables which are not continuous. That means the derivatives at these integer variables do not exist. So we cannot solve the KKT conditions to obtain the optimum. The common used method is the branch and bound method. Let's introduce this method. This branch and bound method is the most widely used and probably the most successful method for solving both integer programming and mixed integer linear programming problems. The basic idea of this method is to solve the problem as if it contains only continuous variables. If the optimal solution contains non-integer values for some integer variables, then use partitioning method for these integer variables to divide up all the possible solutions into subsets. This method also uses bounding methods to avoid exhaustive search. These are the basic idea of this method. How can we understand this basic idea of this method? Let's use one example to help understand the basic idea of this branch and bound method. Let's look at this simple example. In this example, we want to maximize the objective function, that is 3 times x1 plus 2 times x2, subject to some inequality constraints. x1 is less than or equal to 2, x2 is also less than or equal to 2, x1 plus x2 is less than or equal to 3.5. x1 and x2 are both non-negative. Also, x1 and x2 are integer variables. That means all variables in this optimization problem are integer variables. So this optimization problem is an integer programming problem. To be convenient, we use a variable z to denote the objective function value. As we mentioned, one basic idea of this branch and bound method is to solve the problem as if it contains only continuous variables. How to achieve this basic idea, as we have discussed in this integer programming problem, x1 and x2 must be integer variables. These are integer restrictions on x1 and x2. If these integer restrictions are removed or ignored, then x1 and x2 are non-negative and continuous from 0 to positive infinity. By doing this, this integer programming problem becomes a linear programming problem. This linear programming problem is also called the linear programming relaxation of the integer programming problem, or it is called the relaxed integer programming problem. We can solve this linear programming problem using the graphic method or using the simplex method that is introduced in topic 17. Here, let's solve this LP problem using the graphic method. This is because this linear programming problem has only two variables, x1 and x2. We first draw the graph of the feasible region, which is constructed by these inequality constraints. The feasible region is in this pentagon A, B, C, E, O. We also need to draw the contour of the object function. As we discussed before, we can try different values like 3, 7, and 9. For each value, we can draw a straight line like this dotted straight line. Then we can draw a number of dotted straight lines. These dotted straight lines are the contour of the object function. When the straight line passes through the point B in the feasible region, the object function value is maximum, which is equal to 9. This maximum value of the object function is also the upper bound for the object function of the original integer programming problem. This is because this linear programming problem has a larger feasible region than the original integer programming problem. From this solution, we can see x1 is equal to 2, which is an integer, but x2 is equal to 1.5, which is not an integer. That means this solution is not a feasible solution for the original integer programming problem because the integer restrictions on x2 is not satisfied. How can we find an integer value of x2? As mentioned before, another key idea of the branch-bound method is that if the optimal solution contains non-integer values for some integer variables like x2, then use partitioning method for these integer variables to divide up all the possible solutions into subsets. That means we need to partition x2 to examine other integer values of x2 that are larger or smaller than 1.5. So we divide all the possible solutions of x2 into two subsets. One is x2 is less than or equal to 1. The other subset is x2 is greater than or equal to 2. Then we have these two constraints. For x2, we can add each of these two constraints into the original linear programming problem and create two new linear programming problems. Let's say LP2 and LP3. In LP2, we add the constraint x2 is less than or equal to 1. In LP3, we add the constraint x2 is greater than or equal to 2. We can solve these two new linear programming problems individually. We continue to use the graphic method to solve them. Let's look at LP2 first. The feasible region of LP2 is this rectangle. These dotted straight lines are the contour of the object function. From this graph, we can see when the dotted straight line passes through this point, the object function is maximal, which is equal to 8. The optimal solution to this LP2 is x1 is equal to 2 and x2 is equal to 1. Both are integer. That means this optimal solution to LP2 is also a feasible solution to the original integer programming problem. This feasible solution is also called a feasible integer solution to the original integer programming problem. But this feasible integer solution cannot be called the optimal integer solution to the original integer programming problem. This is because we don't know if there is any feasible integer solution from LP3 that will lead to the object function value being greater than or equal to 8. So we need to continue to solve LP3. This is a graph for LP3. From this graph, it is not difficult to determine the optimal solution to LP3 is x1 is equal to 1.5, x2 is equal to 2. The maximum objective function value is equal to 8.5. x2 is an integer, but x1 is not an integer. That means this optimal solution to LP3 is not a feasible solution to the original integer programming problem because the integer restriction on x1 is not satisfied. Based on the basic idea of the branch and bound method, we need to continue to partition x1 to examine if there exists an integer solution to LP3. We need to partition x1 to examine other integer variables of x1 that are larger or smaller than 1.5. Then we can divide all the possible solutions of x1 into two subsets. One is x1 is less than or equal to 1. The other subset is x1 is greater than or equal to 2. We also add each of these two new constraints to LP3 and create two new LP problems. Let's see LP4 and LP5. In LP4, we add this new constraint x1 is less than or equal to 1. In LP5, we add this new constraint x1 is greater than or equal to 2. Then we can solve these two new LP problems individually using the graphic method. Let's see the solution to LP4. This is a graph for LP4. The optimal solution to LP4 is x1 is equal to 1 and x2 is equal to 2. The maximum objective function value is equal to 7. x1 and x2 are both integer. They are also a feasible solution to the original integer programming problem, but it is not better than LP2. This is because the maximum objective function value from this LP4 is equal to 7, which is smaller than the maximum objective function value from LP2. We can also solve LP5. However, there is no feasible solution to this LP5. This is because in LP5, we have this constraint x1 is less than or equal to 2, and also we have this constraint x1 is greater than or equal to 2. That means x1 can only take value 2. Similarly, we also have the constraints for x2. x2 is less than or equal to 2, and also x2 is greater than or equal to 2. That means x2 can only take value 2. However, when x1 is equal to 2 and x2 is equal to 2, this constraint is not satisfied. This is why there is no feasible solution for LP5. As you can see, we solve a sequence of linear programming problems based on the idea of the branch and bound method. The sequence of LP problems solved under the branch and bound procedure may be presented in the form of a tree diagram. This is a tree diagram. Each LP subproblem corresponds to a node like this node. LP1 as a node, LP2 as a node, LP3 as a node, LP4 as a node, and LP5 corresponds to a node and represents a relaxation of the original integer programming problem. These nodes are numbered based on the sequence in which the LP subproblems are solved. As we have discussed, we first solve LP1. So LP1 corresponds to the first node, node 1. This node is the starting node of the tree. It is also called root node or initial node of the tree. Then we solve LP2 and LP3. We first solve LP2 problem. This LP2 is also a node which is numbered as node 2. LP3 is also a node which is numbered as node 3. After that, we solve LP4 and LP5. LP4 is numbered as node 4 and LP5 is numbered as node 5. From this tree diagram, we can see node 2 and node 3 are children of node 1. So node 2 and node 3 are called the child nodes of node 1. And node 1 is called the parent of nodes 2 and 3. Similarly, node 3 is the parent node of nodes 4 and 5. And nodes 4 and 5 are the children of node 3. These two nodes, 4 and 5, are called the child nodes of node 3. We can also see node 1 is the ancestor of nodes 2, 3, 4, and 5. Any node in nodes 2, 3, 4, and 5 is a descendant of node 1. We can also see nodes 2, 4, and 5 have no children. These three nodes are called terminal nodes or leaves of the tree. Node 3 has the parent node and the child nodes. It is also regarded as an intermediate node. Based on this, each tree of the solutions have root node, intermediate node, terminal node, or leaves. Every path from the root node to a terminal node defines a complete solution. The optimal solution should be chosen among all these terminal nodes. That means the optimal solution should be chosen among all terminal nodes. That means the optimal solution should be chosen among node 2, node 4, and node 5 in this tree diagram. As we have discussed, at node 1, the LP1 problem is solved and we get a solution for x1 is equal to 2 and x2 is equal to 1.5. Then this variable is partitioned and two new LP problems are created, which are represented by node 2 and node 3. The process of creating these two new LP problems is called branching. Similarly, after solving LP3, x1 is equal to 1.5 and x2 is equal to 2. Because x1 is not an integer, this variable x1 is partitioned and two new LP problems, LP4 and LP5, are created, which are represented by node 4 and node 5. The process of creating these two new problems, LP4 and LP5, is also called branching. Based on the tree diagram, we have several remarks. We have already discussed these remarks just now.